So our next job is to start looking at how we handle multiplication and division. There's probably a lot more multiplication and division in chemistry than there is addition and subtraction. So it's important that we understand the rules for those too. And this is where significant figures come into play. With addition and subtraction, we don't really think about significant figures or mention that term at all. It's all talking about decimal places, determining how you round off your answers. For multiplication and division, it's all about significant figures. And so you first need to understand what those are before you can really go on and start using them in the rules of how we handle rounding our answers when multiplication and division is in place. So what's a significant figure? First of all, significant figure is basically the values, numbers, or digits in a measured value that you're certain of. In other words, when you make a measurement of mass or volume or temperature or something, and you write it down in your lab book, which digits, which numbers in that value are you certain of, and which ones are you estimating, and which ones are you leaving off? When we look at a calculation, we need to be able to evaluate the numbers that you're putting into your calculator to determine how many significant figures are in each one. Defining significant figures is probably harder than actually figuring out how many significant figures there are. So don't worry so much about the definition, but the skill. It's the skill that's going to matter with significant figures, to where it needs to become automatic. In chemistry, and as many of you hopefully go on to physics, you'll need to use significant figures there too. So what are significant figures? Let's look at a value or two and go through an example of how you determine how many significant figures are in a value, because that's an important quantity to know. It's an important piece of information you need to come up with quickly. So what I'll show you here is a method of figuring out how many significant figures are in a value. Using the United States map and its neighboring oceans as sort of the guide. This is a sort of a device for figuring out significant figures that Mrs. Smallbeck showed me, and I think she heard it from someone else way back when, and so good ideas get passed on, and this is one I'm giving to you from her and from whomever gave it to her. In significant figures, the easy way to think about how many significant figures are in a value is to use the ideas of our oceans. The first idea would be that if you have a decimal point absent in your value. In other words, if you're looking at a number that does not have a written decimal point, then you'll start counting significant figures from the Atlantic side of the value. In other words, from the right side of the value. So if we look at a number and figure out how many significant figures it has, the easiest way to think about it is there a decimal point absent, or is the decimal point actually written and present? If it's absent, you'll start from the right-hand side, or the Atlantic side of the number, and start counting from there. And I'll show you an example in a moment. If there's a decimal point present and showing in the number, actually written there in print, then you'll start counting from the present or the Pacific side of the value. Start counting from the left. And I'll show you some examples to kind of make sense of this. But when it's present, you start from the Pacific side of the number on the left, and when that decimal point is absent, you start from the Atlantic side on the right side of the value. So let's look at some examples. And when you get started counting, then you'll see what we come up with for answers in the process. So here's a good example, 15.076. The decimal point is present. You can see it right there in the middle of the number, right? So we've got this decimal point here, 15 point, there it is, 076. So as we start looking at counting significant figures in this value, we'll start from the Pacific side, from the left side of the number, and go from there. We won't start from the other side, the Atlantic side. We're going to start counting from the Pacific side of our value. And so from the left to the right, cutting across from left to right, we'll start counting with the first non-zero. Here's a non-zero, 1, 5, 0, 7, 6. We start counting at the first non-zero, which in this case is 1, and we go all the way across to the other side of the number, falling off into the other ocean essentially. Start counting at the first non-zero, 1, and count every digit after it until you get to the end of the number. So I'm counting these numbers off. This is 1, 2, 3, 4, 5 significant figures. 5 total significant figures in this value. In other words, we are certain of all the digits in 15.076. 15.076 has 5 significant figures. The 15076 are all significant figures. I started counting again from the Pacific side across to the Atlantic side, and starting from left to right with the first non-zero. I'll show you another example. 10,500. Okay, 10,500 does not have a decimal point present. There's a comma in there, but there's no decimal point. Now you're thinking, well, it would go right here. You can't draw it in. If it's not written there, if it's not printed there, then it's not present. And we would treat this number as a value that has a decimal point absent. And so we're going to start counting from the Atlantic side, working our way across. We're going to start from the right and go toward the left, counting this way. Starting at the first non-zero, start counting at the first non-zero, and go to the other end of the value. So as I come across, to here, okay? I'm going to start at the right-hand side and work across and start counting at the first non-zero. Here's a non-zero, and keep going across from there, across the other side. 1, 2, 3. Now I'm counting in reverse because I'm counting from right to left. I don't count this. I don't count this. I start with the first non-zero, okay, which is my 5 here, and go across to the other end of the value, counting everything else that's there. So 1, 2, 3 significant figures total. The 5 is significant, the 0 after in front of it, and the 1 in front of it is significant. 3 significant figures in this value. Now what does that mean? The zeros we're saying are not significant. So what does that mean for them? What this number is basically telling us is that we're estimating or rounding off to the hundreds place in this number. Someone has rounded this off to 10,500. That's kind of how we want to treat it. Now, it may not be exactly the case that someone rounded it off or that you rounded it off, but that's how we treat this number in terms of its precision. You're only certain to the hundreds place, to the 5's position here in this number. This number could have been 10,514. It could have been 10,484. Could have been something around 10,500 that's been rounded off to the hundreds place. It's a kind of a thing we do when precision maybe isn't as necessary. And so in this case, we can't say that this is exactly 10,500. We'd say it's approximately 10,500. And because that 5 is our last significant figure on the number, and the zeros are there just to fill it in and show that we've rounded, we just say it's got 3 significant figures. If this number were written as 10,514 or 10,484, then we'd be able to count those last digits as precision too, or having precision as well. In this case, it's essentially saying that we've rounded it off to the hundreds place. One more example, and we'll go through a few more together. 0.03080. Now the decimal point is present. Okay, we've got a present decimal point here. So we're going to start counting from the Pacific side with the first non-zero digit and count everything after it. So coming across from left to right. This is a 0. We need to start counting with the first non-zero, right? Which is in the 3's position right there. So we wouldn't count this. We wouldn't count this 0, but we would count the 3, that's 1, the 0, 2, the 8, 3, and the 0, 4 significant figures. This value has 4 significant figures. And we're sure of the 3080. Okay, we're certain of the 3080. You could read this number as 0.03080, or you could read this number as 3080, right? 100,000ths of a digit, or 100,000ths of a unit. We think about 100,000ths as something we don't think about since grade school, but that's essentially what we're saying here. The 0 is in the 100,000ths position, and we're sure that there are none in that spot. So it's another way of thinking about precision as a sort of a fractional idea. So we wouldn't count the zeros on the left because starting from left to right, those don't count. Okay, we're starting from left to right at the first non-zero. What are these numbers doing here then? What is this 0 good for right here? All it's doing is filling that position and keeping it occupied as a sort of a seat holder or a placeholder. So is this 0 in the 10th position. It's these zeros and the decimal point are sort of bumping the 3080 over to where they belong. Without the 0.0 there, you'd have 3080. And hopefully you see that the difference between 3080 and 0.03080 is big. It's a big difference, right? Completely different scale of number. And so by putting the 0.0 in there, they sort of bump the values that count over into position where they belong. So this number has 4 significant figures. Here's a few more examples just real quick for you to practice. How many significant figures in each of these? Okay, on the first one, 34.4, the decimal point is present. So we're going to start counting from left to right. 1, 2, 3 significant figures. I'm going to switch my pen so I can see a little bit better as blue here instead of black. 3 significant figures. Okay, because the decimal point is present, we start from the left. In this example, the decimal point is present again, so we start from the left. 1, 2, 3, 4. Again, starting with the first non-zero, we get 4 significant figures. In the next example, the decimal point is absent. So we're going to start counting from right to left and start with the first non-zero. Not this one, but this 7 and this 2 gives us 2 significant figures, okay, in that value. 903.2, the decimal point is present. So we're going to start from left to right. 1, 2, 3, 4. Again, starting with the first non-zero, we get 4 significant figures. 5.10, decimal point is present. Start from the left, starting with the first non-zero and everything after it. 3 significant figures. Okay. On the other side, 800.0, again, a decimal point is present. So I start from the left. 1, 2, 3, 4. All those values are precise. On the next example, 0.023, the decimal point is present, so I start from the Pacific side, the left, with the first non-zero. So we don't count the 0 here, we don't count the 0 here. We're going to count the 2 and the 3, 2 significant figures. Okay. And similarly on the next example, starting from the Pacific left side, I don't count the zeros. Until I hit that first non-zero, I don't count anything. So these last 2 digits do count, 2 significant figures. Our last 2 examples, the decimal point is absent, so I'm going to start from the Atlantic side with the first non-zero. That means these are significant, 3 of them are, and these other ones would not be significant. So 3 significant figures in this example. And finally, from the Pacific side, okay, don't count this, don't count this, don't count this. Start counting with the first non-zero. So 2, 5, 0. 3 significant figures. So notice again, I mark with the arrows on here the side I'm starting from, and then I always begin counting significant figures with the first non-zero. That's it for introduction on significant figures and figuring out how many are in a value. We'll start using those in our multiplication and division in the next video. Thanks. I just want to show you here some values that have one significant figure. This is a lot of different numbers that you might encounter in a problem or that you might measure. And each of these has one significant figure. 3,000, 40, 40,000, the number 7, 60, 500. Each of those has one significant figure. And in each example on the left, you can see here that there's a decimal point absent. Right? There's no decimal point on any of these. So on each of these, we would start counting from the Atlantic side of the number, counting from right to left, counting from right to left. On each example, we would start counting from the right, from the Atlantic side, and then count across, starting at the first non-zero. Well, in that case, these zeros wouldn't count. This one would. That's a significant value. Starting from right to left, we don't count the zeros. We start with the first non-zero. That would be the 4. Same here, the 4. The 7, the 6, the 5, all the zeros here come before the first non-zero as we count across from right to left. So we wouldn't count those zeros as significant figures. However, on the other side, let me just clear these arrows off real quickly. On the other side of the sheet here, we've got 0.0005, 0.009, 0.04. Each of these values has a decimal point present. So we would start counting from left to right across. From left to right across, starting with the first non-zero. And that's this 5, that's this 9, that's this 4, 4, 3, and this 9 way out here. All the zeros that you see in front of those numbers are simply bumping those significant digits over to where they need to be. And so they don't count as precise. When the decimal point is present, you start counting from the left, the Pacific side. When the decimal point is absent, start counting from the right, or the Atlantic side. In a similar way, each of the values on this page have 2 significant figures. You can count them in much the same way. So the decimal point really matters. And that's an important idea to get across, that the decimal point really does matter. In each of these examples, 80, 80, 80, 80, 80, these are all 80? Well, they're all different in terms of precision, because by putting the decimal point on and then adding zeros behind it, we've added more and more certainty, more and more precision. In other words, we're sure to a greater and greater decimal place. There's a big difference in precision between 80 here and 80.000. You could look at those two numbers and say, gosh, which of these looks more official or looks more precise? 80.000 is very precise, whereas 80 is kind of an approximation. Okay, I have about $80, or I have exactly $80, 80.00. Maybe I have $77 and I say about 80. Maybe something has a volume of around 80 milliliters. Well, you'd be much better off if you knew it was precisely 80.00 or 80.000 milliliters, because your certainty is greater. Of course, getting more precision usually means buying more expensive equipment and getting better values from better equipment. Often in lab, we'll try to use the best devices we have available and make the most of the measurements from them. So this decimal point really does matter. Even just here, where the decimal point is added, by adding that decimal point, it gives us a little bit more certainty than without it. I'm going to clear this off, okay, and look just at these first two examples. If we're counting significant figures on 80 versus counting significant figures on 80 point, that decimal point matters, because when the decimal point is absent, we're going to start counting from the right across to the left, and we're going to have one significant figure, one sig fig. When the decimal point, as you see in the second value, is present, we're going to start counting from the left. And that means the 8 and everything after it gets counted. So there are two significant figures. Having two means having more precision, okay, in the second value. So that makes 80 point more precise and a better value than just 80. So when you write a decimal point, make sure you mean it. And when you need to have the decimal point there, make sure you do. Okay. One more good example of that is 1,000 versus 1,000 point. 1,000 here has one significant figure, whereas 1,000 point has 4. That's saying that we're very sure. Okay. Now our school has students in it. Let's say that you had a school that had about 1,000 students in it. If someone walked up to you and said, "How many students are in your school?" and you said, "About 1,000," they probably know you don't mean exactly 1,000. If you meant exactly 1,000, you could say so. Precisely 1,000 students. That would be kind of unusual if we had a perfectly rounded number of students in our building. Our building maybe has 1,400 students or 1,300, and I might tell someone that. They know I'm kind of rounding it off. If I said 1,304, that would be very precise. So to show that you mean exactly 1,000 in this case, on the example here, we'd need to put the decimal point in place.